Hello, welcome to another how-to video. Today we are going to look at one of the most common peripherals we use in our projects, the keypad. Now, keypads are essential accessories to most systems with human interaction, and one of the easiest one to program is the 4x4 keypad with 16 keys. The keys are from 0 to 9 with two special characters, a layout common to telephones with an additional keys for A, B, C and D for special input. The readout mechanism for all these keys are still the same. There are 8 output pins, 4 of them representing the 4 rows and 4 of them representing the columns. When a key is pressed, the microcontroller needs to detect the row and column that has experienced transition in signal levels to identify the exact key. Looking at the circuit, we can see that each button is connected to one row and one column, so every key has a unique row-column combination. The reading mechanism involves supplying a signal from one of the row pins and detecting the signal at the column pin. This can be easily accomplished by controlling the GPIO pins on our array board. The scan mechanism can be expressed in a flowchart as shown here. We start by setting the row output to 0. In a loop, we keep checking whether a button is pressed by reading the column state. If a key has been pressed, then one of the columns will read 0, being shorted with the row. The pressed key is located in this column, so we register that position. Next, we scan for each row for every column. To do this, first we make all the rows high and then make it low one by one. By default, the column pin is read high. So, when a row is made low, it is instantaneously recognized with the prior knowledge of the pin that has been set low. At this point, the row number is identified. Having obtained both the row and column number, the location of the key can be found at the intersection. To connect the keypad to an EK board, the most suitable location is the Arduino connector area. We have got 8 GPIO pins in a line without any interruption. So we can connect the pins from the keypad to pins D2 through D9. The first 4 pins of the keypad are connected to R1 to R4 and the next 4 are connected to C1 to C4. A key mapping is shown in this slide. R1 to R4 is then connected to the MCU via D9 to D6 and C1 to C4 is connected via D4 to D2. In terms of key configuration, the row pins are set up as output pins and column pins are set up as input pins with a pull-up resistor. Now we can move on to building the project. First, we give a name to our project. Then we select the board EK-RE6M4 as usual. For the rest of the configurations, we don't need to change from the default, so it is a flat executable project with no OS. Once the project has been loaded, we need to configure the pins. Since this project requires only I/O pins, we don't need to add any additional stack. Let's review the key map again. We need to locate these pins by their pin numbers in the configurator. So, we need to configure 8 pins, 4 as input and 4 as output. Let's start with the first pin for R1. We can see that this pin is named Arduino_D9. We shall keep it as it is for easy referencing in the code. The mode is already set to GPIO output. We do the same for R2 and R3. For the fourth pin, R4, we can see that the default name has additional labels. So, we change it back to Arduino D6. An important configuration to note here is the mode for this pin, which is set to peripheral by default. As it turns out, this pin is being used by one of the timers. So we can navigate to that particular timer configuration and detach this pin. It makes the pin available for reconfiguration. We can now make it an output pin. Next, we need to configure the input pins, which should be labeled as Arduino D5 to Arduino D2. We also enable an input pull-up for these pins, being provided by the MCU. We can then generate the project contents. In our code, the first variable is an array which is used to hold value for the key presses to be identified by the columns. So we need 4 elements and the data type is the BSP IO level, which is defined in the BSP IO header file. Then we shall have 2 variables to hold the location of the row and column. Another variable to hold the return status of different API calls, which takes the fsp_er_t data type. Let's look at the keypad layout again. We need to map these keys to the input we detect from our program. So we make a character array and name it key map. This array would be arranged similar to the key layout, and each key can be referenced by their index, which is essentially mapped to the row and column number. Next, we are going to add a character variable to store the final input of the keypad, and then we are going to declare a few functions. We need functions to set all the row pins to high and then set all the row pins to low. We also need a function to read the state of the column pins. Then we need a function to check if a key has been pressed, and then a function to scan for key press. For the write rows high function, we are going to set all the pins connected to the rows to high. We are going to pull the pin write API from developer's assistance. Then designate the pin number. In this case, it can be set by its label Arduino D6. The key state is written as BSP IO level high. Since this is an FSP function, we can use an assert macro to make sure the return for this function call is a success. We will then proceed for the rest of the pins, which are D7 to D9. Similarly, we create a write rows low function where the pin state is set to BSP IO level low. Next, we shall define the read columns function. This implementation will use the pin read API and store the reading in the column array variable. When a key is pressed, that is grounded, the low reading will produce a 0 value and store it in the array. The if pressed function will simply check the values in this column array and return 1 if any element in the array is 0, meaning a key has been pressed. Now we can proceed to the hull entry function. In this function, we shall create a while loop and run the key scan function. We have not yet defined this key scan function, so let's write it. The first execution is the read columns function, which will read the state of the columns pin. Next, we shall run the if pressed function to see if any key has been pressed. If a key has been pressed, we shall execute the key scanning mechanism. We have also implemented a soft debounce procedure that double checks the key press after 50 millisecond delay. Now, as we have already registered a key press by scanning the columns, we shall store the location of the column first. The column which has rendered a 0 value is the column where the pressed key is located. Next, we are going to check for the row. We will go row by row for this procedure. For each row, First, we are going to make all the row pins high. Then, we are going to make only one row pin low. If the row of the pressed key and the row that has been made low is not the same, then all columns will read a high value. This is because the row that is low is not shorted to the column pin, and the column pin is by default pulled high. But if a key is pressed, then one of the columns will read a low value, so we can identify the row position from the pin that is currently set at low. So this procedure will give you the position of the row and columns for the button that has been pressed. We shall store the location and then format the location to the index of the key map we have made earlier. The location of the key is used to store the key information in the input variable. After half a second delay, we shall make all rows low for the next scan. At the end of the function, we shall also reset the value of the row and column and make the input as an empty character. So, at every scan, if no key has been pressed, the input value is seen as an empty character. We can build and debug our program now. In the Expressions tab, we can see the value for the row, the column, and the input character. So, that is a demonstration of how we can integrate a 4x4 keypad with the array boards. See you in the next video.